Welcome back to the channel. Do you remember the agent work we did in the 4 videos? We built the React loop from scratch first, then we abstracted it with LangChain. We then gave it explicit state and control flow with LangChain. We also split it into specialized roles with CrewAI. And in every single video, the agent knew exactly one thing about the world, which is whatever we hard-coded into the tool functions, which was Tokyo population and Japan's population. These were static strings in a Python file. That's not an agent, that's a calculator with just a few extra steps. But we know that a real agent, the one you would actually ship to production, needs to answer questions about your data and about your documents and about the knowledge base and sometimes about your company's internal information that no LLM was trained on and no web search can find. So that's the problem RAG solves. In this video, we are not going to build RAG from scratch. I already have a full series on that and I link every relevant video throughout this one. What we are going to do is answer the question that my RAG series doesn't cover. The question is, how does RAG actually fit into LLMOps stack? Not how does RAG work mechanically, but where does it live in your production architecture? When does your agent need it and when it is an overkill? How do you connect a RAG pipeline to the LangGraph agent that we built in our video 5 or CrewAI video that we built in video 6, and what breaks in production and why? That's what this video is about, and this is the memory and knowledge layer of LLMOps. Let's get into it. Let's take a moment to understand where memory fits in the LLMOps stack. Layer 1 was application layer. Layer 2 was orchestration, which we covered from video 3 through 6. That covered how do you coordinate agents, tools, and control flows using raw Python, LangChain, LangGraph, and CrewAI. That layer was complete. Then we moved to model layer, which was next in the stack. Then comes layer 4, which is memory and knowledge layer. And this is what we are starting today. So let's understand memory a bit more. There are 3 types of memory in an LLM system. The first one is in-context memory. This is the message list or the conversation history passed to the model on every call, which includes every message the user has sent, every response the model has returned, every added state. It exists inside the prompt and it's bounded by model's context window. For example, 8,000 tokens for llama on Grok. When the conversation ends or the context window fills, this memory is gone. There is no persistence, so nothing survives beyond the current session. The second type of memory is working memory. If you remember the memory tool we built in the agent series, this is what this memory is. A Python dictionary that the agent writes to and reads from during a single run. It exists for the duration of one agent execution. When the agent run completes, the dictionary is discarded. It is scoped to a single task, not the full conversation or a session. The third type of memory is external memory. This is persistent storage outside the model and outside the run. These could be the documents in a vector database, records in a relational database, or embeddings indexed from your internal content. The agent queries this storage at runtime and retrieves relevant chunks and injects them into the prompt as context. The storage persists independently of any individual run or conversation. When the documents update, the storage also updates. The model weights do not change. RAG is the retrieval mechanism for that third type of memory. It is a pattern that connects a live agent request to a persistent external knowledge base. These 3 types of memories are not interchangeable. In-context memory handles conversation continuity within a session. Working memory handles intermediate values within a single task, and external knowledge handles persistent domain-specific information that the agent needs across all sessions and all tasks. I have a dedicated RAG series on this channel. There are 10 videos covering the full pipeline from fundamentals to production. If you are new to RAG, that series is the foundation, and this video assumes that you understand how RAG works. And if you do not, please start there. Let me walk through the series so you know which video applies to where you are. Building a basic RAG pipeline from scratch. This is the entry point. It covers chunking, embedding, vector storage, retrieval, basically the complete pipeline built from first principles. If you have not built a RAG pipeline before, this is where to start. The next one I want to show you is chunking and context windows in RAG. This covers what chunking is and its various types like fixed chunking, structural chunking, LLM based semantic chunking with code for each. Chunking strategy determines what the retrieval will see at runtime. Chunking strategy determines what the retriever can find. A retriever operating on poorly chunked documents will return irrelevant context regardless of how good the embedding model is. If you want to learn how to improve the retrieval quality, this is what you should watch. Next is advanced RAG, which includes hybrid retrieval, re-ranking, and context selection. This is the highest viewed video in this series, but for a good reason. Dense retrieval finds semantically similar content. Sparse retrieval like BM25 finds the exact keyword matches. Hybrid combines both and re-ranks the merge results by relevance score. This is the retrieval architecture for production systems. Basic dense-only retrieval misses too many relevant chunks in real document collections. Next one is designing RAG ingestion pipelines with Dagster. In this video, the ingestion side, including extracting, chunking, embedding, and indexing, built as a proper orchestrated pipeline with observability rather than a script only, which we performed in the videos before this. If you are building RAG for production, this is an operational pattern because you need an ingestion pipeline to keep up with ever-changing knowledge bases. The next video is about RAG ingestion deep dive, which includes chunking identity and content hashing. This video covers how to detect changed documents and re-ingest only what is new without creating duplicate vectors. This is the operational problem that appears the first time your source documents are updated and you need to re-ingest without corrupting your vector database. The next video is about auditable RAG on AWS. We cover concepts like idempotent ingestion, versioned knowledge, and traceable AI decisions. How to make sure that every retrieval is logged, every answer is traceable to the source document chunk that produced it. This is the architecture for regulated domains like healthcare, legal, financial, where you need to answer the question, why did the agent say that and which document was it based on? The next video is about RAG evaluation, measuring retrieval, grounding, and drift. We cover matrices like recall at K, mean reciprocal rank, faithfulness score, hallucination rate, context coverage, and metrics drift over time. How do you know your RAG system is working correctly after you ship it? This connects directly to the evaluation layer of LLMOps series coming later. The next video covers how I improve recall at 5 from 0.4 to 0.9. This video shows a concrete retrieval improvement case, specific changes to chunking strategy and retrieval method that moved the metric from 0.4 to 0.9. If your RAG pipeline is returning wrong chunks, this video shows where to look. The next video is about how I reduced hallucinations in a RAG system by 60%. This video shows hallucination reduction through grounding. Once retrieval is returning the right chunks, the next problem is the model ignoring them and answering from training data instead of the retrieved chunks. This covers grounding instructions and faithfulness constraints. The last video is LangChain RAG explained. Obviously, this covers main LangChain concepts like chains, memory, agents, and why the architecture matters. How to use LangChain integration layer for the pipeline with a Python demo. This is the full series. Links to every video are in the description, grouped by where you are in the RAG journey, like foundation, production, quality, and enterprise. Now let me connect all of that to the agents we built. So you can see that this is our LangGraph agent that we built. For LangGraph, RAG connects at tool layer. Basically, RAG becomes a tool and the agent decides when to call it in the same way it decides when to call a web search or a calculator tool based on the tool description and the question context. The graph doesn't change. The routing logic or agent state, they don't change as well. The only change is that you need to add a new tool and the agent has access to your internal knowledge base. The tool implementation is just a function similar to any other tool implementation, and it takes a query string. Let me paste this code here, which is our RAG tool. So this is what it is. So the function takes a query string and run it against your vector store and returns the retrieved chunks as a string. There is one design decision worth making explicitly, which is one RAG tool versus multiple. A single RAG search function, which is a tool, is appropriate when your agent operates over one knowledge base with one domain and one retrieval strategy. Multiple tools are appropriate when your agent needs to search distinct knowledge domains with different retrieval characteristics. A customer support agent that searches product documentation and order history separately, those are two different retrieval strategies and two different vector stores, two different tools. The LLM routes to correct tool based on the question context and the tool description. This also gives you separate observability per domain, and you can measure retrieval quality on product docs independently of the order history. Let's move to the CrewAI agent and connect RAG to it. In the CrewAI agent, connection point is different and the design decision is more explicit. In a multi-agent system, tools are scoped per agent. The researcher, which is here, had web search and memory store tool, and the calculator had memory retrieve and calculator. Adding RAG means deciding which agent gets the retrieval capability. For most Crew design, RAG belongs to the researcher. The researcher's role is information gathering, including web search, storing the information, or RAG for internal data. Adding RAG search to the researcher's tool list extends that role without changing the Crew architecture. For complex crews with multiple knowledge domains, a dedicated knowledge retrieval agent is a cleaner pattern. In normal cases, you define the tool, the RAG search tool, and connect that to your researcher so that it has access to the internal knowledge base. But if you want to define a dedicated knowledge retrieval agent, this is the way you define it. I'm going to paste some code here. So you define a knowledge agent and you give it a role, which is knowledge retrieval specialist, and then similar to the other agents, you define its goal and tell the backstory and then give it access to the RAG tool. A dedicated retrieval agent isolates the RAG concern completely. The reasoning agent, which is researcher, receive retrieved context as task input. They do not interact with the vector store at all. And this separation means that you can improve the retrieval strategy and swap dense for hybrid, add re-ranking, change chunk size without touching any of the reasoning agents. The interface between retrieval and reasoning is the task context handoff, which doesn't change. There are 3 failure modes specific to RAG agents in production. Each one is covered in depth in the RAG series. I'll point to the relevant video for each. The first failure mode is that the retriever returns wrong chunks. The agent calls RAG underscore search function that we just defined. The retriever returns 5 chunks and the LLM produces an answer from those chunks. The answer is wrong. Not because the model hallucinated, but because the retrieved chunks were adjacent to the correct answer rather than containing it. The model reasoned correctly from incorrect evidence. This is a retrieval quality problem. The solution is in chunking strategy and retrieval method. If your agent returns wrong answers, measure retrieval quality first. For example, recall at k on a test set before touching the prompt or the model. The recall improvement video is in the series, covers this directly. The second failure mode is the agent ignores retrieved context. The retriever retrieved 5 relevant chunks. The model responded using its training data instead. This is the grounding failure. The model has not been sufficiently constrained to answer from retrieved context only. The fix is explicit grounding instruction in the system prompt. That is, answer only from the provided context. Do not use prior knowledge. And if the context doesn't contain the answer, say so. The hallucination reduction video covers all this. The third failure mode is the knowledge base goes stale. Documents were ingested 3 months ago. Those documents have since been updated and the agent retrieves the old version. The answer was correct 3 months ago. There was no error, no exception. The agent simply returns the outdated information. This is the idempotent ingestion problem. Without a re-ingestion strategy that detects changed documents via content hashing, your knowledge base drifts from your source documents silently. The chunk identity and content hashing video covers the detection and re-ingestion pattern. Now, let me put the full picture together. A production RAG agent system has 2 pipelines running independently. First one is the ingestion pipeline that triggers on a schedule or on document change events, that extracts source documents, chunk them using semantic or structural chunking, embeds each chunk using an embedding model, and indexes the vectors into your vector store. Content hashing detects changed documents and re-ingests only what is new. This pipeline runs continuously in the background. It doesn't interact with the query pipeline at runtime. The second pipeline is the query pipeline that triggers on every agent request. The LangGraph agent or the CrewAI agent receives a user query. The agent determines, based on the tool's description and query context, whether the internal knowledge is required. If yes, it calls rag_search function that we defined. The retriever runs hybrid search against the vector store, re-ranks the results, and returns the top chunks as context. The LLM generates a grounded answer from that context. Between those two pipelines, evaluation runs continuously. Matrices like recall at k on a held out test set, faithfulness scores on production responses sampled at a defined rate, and metric drift monitored over time. This is not a post-launch addition, it's a part of the architecture from the very first deployment. Let's wrap up. 3 things from this video. The first one is memory in an LLM system is not one thing. It's in-context memory, working memory, and external knowledge solves different problems at different scopes. The second takeaway is the RAG connects to your agents at the tool layer. The graph and crew architecture from the previous layer do not change. The third is the 3 production failure modes, which includes wrong chunking, ignored context, and stale knowledge base. Each have a specific fix covered in the RAG series. Links to every video is in the description. If it is helpful, please consider subscribing to the channel. I'll see you in the next one.